this interesting question using node analysis method, we have to find what is the ammeter reading, that is what is the current which is flowing through this 2 ohm resistor, and we have to use the node analysis method. So here we see number of nodes are there. This is a node, this is a node, this is node, this is node, this is node, this is node, and this is also node. So we have number of nodes in this question. We can take any node at reference potential. Let's take this, we can take it as 0 volt. So if this is at 0 volt, so we obviously, so this is going to be at plus 100 volt. We can take this at X and we can take this node at potential Y. So if this is at X, this is a battery, there is no resistance over here. So if this is at X, so this is going to be at X plus 50 volt. So if this is at X plus 50 volt, from here to here we see this is a conducting wire. Whether you join this 2 ohm resistor over here or you slide on the conducting wire or you connect it over here, that's one and same thing. So from here to here, so it means it is also at X plus 50 volt, this, and obviously this is also at X plus 50 volt. Because from here to here this is a conducting wire. You can connect it like this, or you can slide and you can move it like this also, that's one and same thing. So it is going to be X plus 50 only. That is, whether you connect it like this or you connect it like this or you connect it like this, it's one same thing. That is, it's going to be X plus 50 volt only. So let's keep the basic network diagram intact and we make it at X plus 50. Now we are considering Y node, and we say I1 plus I2 plus I3 is equal to 0. So for this, I1 is Y minus 0. Y minus 0 is the potential difference, divided by 2. Potential difference by resistance is current, that is I1 plus I2. I2 we have taken in this direction, that is Y minus 100 divided by 2. Potential difference Y minus 100 divided by 2, and this is Y minus X. Y minus X. All the currents, they are going out, so this potential we have taken as a higher as compared to this. So Y minus X, the potential difference, divided by 2 is equal to 0. So this is one equation we get. We can also give names to this node as A, and this we can call it as node B. As KCL is applicable for this node, this node, this node, this node, similarly is applicable for this node, this node, this node also. Now let's apply for node A. So it is going to be current in this direction plus current in this direction plus current in this direction, that is equal to 0. So let's once again call I1, I2 and I3. They are not the same currents which we have done over here. It is just a representation, that is whatsoever the current is this way, whatsoever the current is this way, whatsoever the current is this way, the summation of them, that should be equal to 0. We could have also taken I4, I5, I6, that doesn't matter, because finally we just want the values of currents. So this is going to be, current is going to be 0 minus X plus 50, 0 minus this upon 2 plus 0 minus Y upon 2 plus over here we don't have any resistance. So what we do is, we can simply say, write it as I3 only is equal to 0. So now here we observe that there is value of I3, then this we cannot represent in terms of X and Y. There is no resistance in this arm. Now if we take the value of I3, now we have to do away with I3. So one thing we can notice, if suppose we assume that current is moving in this direction, and that is what we have assumed over here, if the current I3 is coming from here, and let's say it gets divided into I4 and I5. So I3 is going to be I4 plus 5. Once again, we are primarily using Kirchhoff current law only. So far we are taking all the nodes at the highest potential or lowest potential. Now we move one step ahead. That is, this node can be at a higher potential as compared to the other nodes, and it can also be at a lower potential as compared to some other nodes. That is what we see over here when we say current comes here, it gets divided in this and this. Once again we are using Kirchhoff current law, but now we use I3 is equal to I4 plus I5. Still we are using the Kirchhoff current law. Still we are using conservation of charges. Still we say that is, there is no accumulation of charge over here at this node, and there is no generation of current or charges at this node. Whatsoever current is flowing over here, that gets divided into this I4 and I5. So I3 is equal to I4 plus I5. We have done this because over here we don't have any terms in X and Y. When we don't have any terms in X and Y, we have to eliminate I3. We have taken, let's say the current direction is I3 only. So this only gets divided into this and this. Fair enough. KCL, Kirchhoff current law. So I3 is going to be equal to, this is at 100 volt, 100 minus I4 is 100 minus X plus 50 upon 2 plus 100 minus Y upon 2, that is I5. Now we can put this I3 is equal to this into this. So we have all the terms in X and Y. So one equation we have in X and Y is this, the other equation in X and Y are known as this. We can solve these two equations to get the values of X and Y. Once we get the values of X and Y, once we find the values of X and Y, we can find the potential difference across this resistor. Once we find the potential difference across this resistor, we can divide that value by 2 ohm and we can find the current. If the value of X is greater than the value of Y, the current shall be flowing in this direction, and if the value of Y is greater than the value of X, then the current shall be flowing in this direction. And the values I have on solving this equation, X comes out to be minus 25 by 2, Y comes out to be 125 by 2, and the values I have on solving these equations, the X comes out to be 25 by 2, Y comes out to be 125 by 2, so that is, this potential is higher as compared to this potential. We can find the potential difference, that is this minus this, and current through this 2 ohm resistor, that is emitter reading, comes out to be 75 by 2 ampere.